Hello, and welcome to week 4 of Astronomy 20, where we're discussing stars and galaxies. So, at this point on week 4, we've finished covering our 3 introductory chapters. So, if you look over here where I have the syllabus document open, you can see that in weeks 1, 2, and 3, we covered science and the universe, very introductory chapter. We talked about how to discuss things like angular measurements in the sky, which is observing the sky, how to quantify the celestial sphere, some important details there. Then we did a little crash course in Newtonian mechanics and gravity, which was orbits and gravity. Okay, so we wanted to understand, what's the force that holds the universe together? It's gravity, and how do we describe motion? Well, those with Newton's 3 laws. We also talked about Kepler's laws, which are really important for understanding orbits. Okay, now we're now jumping ahead to the main content of the semester, which is stars and galaxies. We'll spend the majority of the time on stars, although galaxies will have their time to shine, literally and figuratively, later in the semester, closer to the end. Okay, so our first chapter on stars is chapter 17. That's why we take a big jump. The chapters in between, 4 through 16, are focusing on the solar system, planets and comets and asteroids and so on. Okay, so we're jumping ahead to chapter 17, and this chapter is about analyzing starlight. There's a few parts of this chapter, which I will, of course, discuss in the lecture video, which you can already watch. And those sections are described here: the brightness of stars, the colors of stars, the spectra of stars, and then using the spectra to measure motion. All right. So, kind of to break that down, the first part is the brightness of stars. That's actually the main quantitative part of the chapter. That the entire homework is based on that section, 17.1. That's where the only equations come up for this chapter. After that is kind of a survey of which is not we'll get into surveying stars later, but kind of a quick summary of some interesting attributes of stars. How do we discuss their color and how that relates to temperature? Hotter stars or blue stars, for example. And then how do we look at gaps in the star's spectra? Which of course begs the what is a spectra? Well, a spectra is a rainbow, essentially. It really is. It's a rainbow, and stars produce rainbows of light. And so then we can look at that, and there's actually little missing spots in that rainbow, and it tells us something about the elements that exist in that star, which then tells us something about the size of star or the life phase of that star. And then, or maybe it's not a star at all, it's a brown dwarf, which is a failed star. So that's a big part of this chapter, and we kind of approach it this way that your textbook does, because historically this is how information was first gained about stars. Interestingly, in the next chapter, then we'll introduce something called the HR diagram, and the HR diagram is really the periodic table of astronomy. So in other words, as the periodic table is to chemistry, the HR diagram is to astronomy. It's the number one document or diagram that tells us everything about stars. But historically, they didn't know that yet. They were kind of building the blocks that eventually became the HR diagram. And that's what this chapter is all about. It's about the foundation that leads to that one very important diagram that tells us so much. But hopefully this will then give us that understanding, so we're not just throwing the diagram and told, hey, memorize this. Instead, what is a spectra? Why is it a rainbow? Why are there gaps? What does that tell us? And finally, I want to get to that last section, 17.4. That one's about motion. And the key word there is the Doppler effect, because the idea is if a light source is moving towards you, it becomes bluer in color. If it's moving away from you, it becomes redder in color. That's because of the Doppler effect and the wave nature of light. If something's moving away, we say it's redshifted because it became redder. It's often not much redder, but it's measurable by scientists using the particular devices that break up light into its wavelengths. So that's going to be one other aspect that we'll talk about. And we'll come back to the Doppler effect. It's actually very important. And we'll continue to discuss it, especially as we get into near the end of the semester, Hubble's law. But that's getting ahead of myself, of course, so we're not there yet. Now, so that's kind of the big overview. I get into the details in the lecture video. Now let's talk about a previous homework and a current homework. Okay, so the previous homework I want to talk about is 2 homeworks back. That's homework 2. This is the one I'm currently working on grading. So let's pull up homework 2. So if you go back to the homework 2 assignment, you'll see now it includes a full solution, just like homework 1. Soon homework 3 will include a full solution as well. Homework 2 was all about angular size, because that was the quantitative, the math part of chapter 2, was calculating angular size based on this formula here, which was R equals, let's zoom in a bit on this, R equals d theta. R is going to be the distance to, or actually no, R is I always mix these up. What happened there? Anyway, so r is the radius. Yeah. So obviously theta is the angular size of an object in radians. D is the distance to the object, and R is the size of the object. So you can see here that the size then is the angular size here, theta max, is that's the maximum angular size, is the radius of the object divided by the distance to the object. So there's the radius of the object, 3,476 kilometers, divided by the distance to the object, 356,400 kilometers. Okay, so it's much further to the object than the size of the object. And what is the object? Well, if you recall, it's the moon. And the idea then is we take the radius of the moon, which is unchanging because that's the actual physical size of the moon. The moon doesn't shrink or expand appreciably at all. All right, it's just a cold inert sphere of rock. Okay, it doesn't even have a molten core. But then we have that information, the size of the moon divided by and that would be the closest distance, the minimum distance, because if you divide by the smallest number, you get the biggest angle, all right? And then, I have it calculated here. There it is in radians, and there it is in degrees. So you can see that the maximum size of the moon is over half a degree. Okay, so if we could convert this to arc minutes, if we were to convert it to arc minutes, it would be over 30 arc minutes, because you have to remember there's 60 arc minutes in a degree. So just because it's 0.5, if we round 0.56 degrees, does not mean it's 56 arc minutes, because 56 arc minutes would be nearly a full degree. So that would be closer to 0.9 degrees. It's the whole idea of, kind of that just like time, that, there's 60 minutes an hour, but that doesn't mean that 59 minutes is 59% of an hour. Far from it, right? It's closer to 95% of an hour. Okay, and then we calculate the minimum angular size of the moon, and that's when the moon is furthest away. So here we have the largest distance rather than the smallest distance. Okay, and in that case, we end up with an angular size that is just under half a degree. So it's 0.48, or rounding to 0.49 degrees instead of rounding to 0.56. So actually, definitely a difference in size, and we notice it. That's why the moon does appear bigger sometimes. It absolutely is noticeably bigger and smaller. Okay, and so then the difference between the angular sizes is represented right here. All right, because that was part of the problem. And then we go on to talk about the sun. So we do the same thing with the sun. And in this case, of course, the sun doesn't orbit us, but we orbit the sun. So sometimes Earth is closer to the sun, sometimes Earth is further from the sun. So we take those two values, the closest approach of Earth to the sun and the furthest. So the perihelion and the aphelion are the terms, okay? So the perihelion is closest, aphelion is furthest from the sun. So we put those values in, and we get angular sizes that don't vary as much. Okay, so the size of the sun in the sky does not vary as much in angular size. It varies from 0.54 degrees to 0.52 degrees. So some variation, but not as much. Okay, and so then we come up with the idea. Then is that could we have an eclipse based on this criteria? And if we look down here, then we can see that it is not possible for a total solar eclipse because the sun is greater than the size of the moon when we're closest to the sun, but the moon is furthest from us. So in other words, the moon would not completely cover the sun, leading to what's called an annular eclipse. And those happen, right? So if the conditions are just right, if during there would be during a new moon, because the moon needs be between us and the sun for a solar eclipse, that during a new moon, the moon happens to be as far away as it gets during its elliptical orbit, or close to as far away as it gets, and we happen to be as close to the sun as we get during our yearly orbit around the sun, then we get an annular eclipse. It's not technically a total solar eclipse because the sun is not completely covered. All right, which is pretty cool. And you don't see the corona during that type of solar eclipse because the actual chromosphere of the sun is so much brighter that we just see that ring of very bright chromosphere. All right, it's the rarest type of eclipse. Okay, so that was question one. If we take a look at question two was also about angular size. In this case, estimating the size of a particular star, Betelgeuse. How big would it be if it was close to us? Because of course it's actually quite far away. But what if our closest neighboring star was Betelgeuse, this remarkably large star? All right. And this is kind of a fun thing to think about. So here we go ahead and calculate the size of the star, which is huge. I mean, these big giant stars like Betelgeuse, which are dying stars. We'll talk about that later when we talk about the life stages of stars. They're red giants, but that means they're dying, right? They're well on their way of becoming a supernova, all right? Leaving a black hole or a neutron star as a remnant. But point being, these giant dying stars like Betelgeuse, they're so big that they actually would engulf Earth's orbit if we replaced our sun with a star that big. They're that incredibly huge. Okay, so we find that huge size, bigger than an astronomical unit, and then we go ahead and calculate how big would Betelgeuse appear in the sky if instead of being a rather distant star, not particularly distant, but thousands of light years away, instead it's only 4 light years away, it would actually appear 7 arc seconds in size. All right, which is really quite large, right? It's about a twelfth of a degree. Okay, and so it would be one of the biggest objects in the sky. It'd be larger than let's see, I think I go ahead and compare it to Venus, but it would be larger than Venus. Venus's angular size in the sky, and we'd see it half the year rather than just occasionally when we only see Venus occasionally during sunrise and sunset. But point being, it would be a dramatic star. People talk about it as by far the brightest star in the sky. Of course, it is still one of the brighter stars in the sky, but it's much more distant than only 4 light years away. Okay, all right, so good. Now, that's a good segue because here I was talking about brightness, but I was using angular size as a proxy for brightness because if a star is bigger, it's going to be brighter, right? It's taking up more space. But actual brightness isn't just size. Stars can be small but brighter just because they're producing more energy. So their size and their brightness are not always directly tied together. And in fact, discussing brightness is the topic of today's homework. Well, this week's homework. So let's go ahead and go back and take a look at this week's homework. All right, so this is homework 4, covering that chapter 17, which I was discussing before. I reflected back on chapter 2, and in chapter 17 and the current homework, we have 2 questions that are both about star brightness. Okay, so if you look here, we have a question that says the star Vega has an apparent magnitude of 0.026, and a nearby star in the celestial sphere named Gaia DR2 has an apparent magnitude of 12.56. Okay, how much brighter does Vega appear to an Earthbound observer as compared to Gaia DR2? What the heck am I talking about there? Well, of course, you have to watch the video and look at the material because the equations are described in the textbook. Okay, now here's the thing. It might seem strange, and it might even seem like a typo because I'm literally saying that Vega, which has a very small apparent magnitude, is brighter than this other star, Gaia DR2, that has a big number, 12.56. How is it that the thing that is close to 0 is brighter than the one that has 12.56? Well, that's the way apparent magnitude works. Okay, so first of all, it's a logarithmic scale. Logs can behave strange like that. And this particular logarithmic scale is based on the idea that the smaller the number, the brighter the star. So the very brightest objects in the night sky have apparent magnitudes that are so small they're negative. All right, so the moon has a negative apparent magnitude. The sun has a negative apparent magnitude. The brightest stars like Vega, arguably the brightest star in the night sky, has an apparent magnitude that isn't quite negative, but is very close to 0. And then as we get into very faint stars, those that are barely visible or not visible to the naked eye, that you have to use binoculars or a telescope to see, that's when we start getting apparent magnitudes around 10 or larger. Okay, so let's take a quick look at that. Let's do a quick, just kind of to justify this, I want to show you the part in the textbook real fast. So this is 17.1. This is the only part you need to refer to solve the math-based homework, all right, which I'm discussing currently. Okay, so if you look down here, here's a table, right? So we can see here's the sun, by far the brightest object in the sky, has an apparent magnitude that is less than -25. Okay, so you can see having a very negative apparent magnitude means really bright. Okay, the moon is the second brightest object in the sky, also has a negative apparent magnitude. And then we get into the planets, so Venus and so on. Sirius, actually, so there is one star, I forgot, there is one star that actually has an apparent magnitude that is negative because it's that bright, and that's Sirius, the brightest star in the sky. Okay, but then we get on to stars like Vega and Betelgeuse, Polaris, right? So other very bright stars in the sky. Excellent. Okay, all kind of clustered around 0. And then we get up to the faintest object that you can see with the naked eye is actually just above 5.6. So actually, once we get to 10, we need binoculars. So this DR2 star, we would need some sort of telescope or something to see it. Okay, and then we get up to a 1-meter telescope. You can see stars up to an apparent magnitude close to 20. So the idea is, as they get fainter and fainter, their apparent magnitude first becomes less negative and eventually just becomes larger and larger and positive values. Okay, that's the apparent magnitude scale. It's good to kind of see it, make sense of it. The equation that drives that scale is this. Okay, here's the apparent magnitude here. This is the differences between apparent magnitude. M for apparent magnitude. And then that's equal to 2.5 times log of the ratio of true brightness. So you see that then. Okay, so what is apparent magnitude? Apparent magnitude is a logarithmic scale of brightness. Well, what is brightness? Well, brightness is, again, just perspective. It's how bright it appears in the sky. So really, both apparent magnitude and brightness are just how they appear to earthbound observers like us. Later, we're going to relate brightness to true luminosity, the actual power output, how much energy comes out of these stars. But of course, we need to know distance to know that. Okay? But we're not, that's what we're not talking, that's not what we're talking about here. We're not talking about true power. Brightness is not how actually bright that star is, because you could have a very, very high energy outputting star that's very far away, so it would not appear very bright to us. So it would have a small value of B, which means it would have a large value of M. So both, again, to reiterate, because this is confusing, I know, both apparent magnitude and brightness are subjective measurements of how bright a star appears in the sky. Then why have two if they both tell us the same thing? Because one of them is logarithmic and the other is not. And the whole reason that we would have one a logarithmic scale and a non-logarithmic scale is because the brightness is vary so much. If we talk about a faint star in the sky, it is about 1,000,000 times less bright than the sun. 1,000,000, a factor of 10 to the 6. Well, that's hard to graph. Imagine this figure if it had a difference of a million. How would you fit that on a number line? That's why we use logarithms, because we can easily fit them on a number line. We can easily graph them. Okay, it's common in science. It's astronomy being no exception. We use logarithmic scales for values that are spread apart over many orders of magnitude, many factors of 10. Okay, all right. So that's the equation. This is what we want to refer to. Let's go ahead and wrap up this video by looking at the homework, and I'll give you 2 tips of how to get started on both of the questions. Okay, so homework 4, going over here. Okay, so here's the homework. I already started talking about it, but I'm going to switch screens to show you the 2 equations to get started. Okay, so let's do that. There we go. Okay, so if you look here, here is the question. All right, and we've got number 1. It's, we want to relate those magnitudes to brightness. So since the question is asking for brightness, I've given the version of the equation that is already solved for brightness. Okay, so here it is. We've essentially already done the work. In my solution, I'll show the derivation to show how to go from exponents to logarithms. It's a review of things you would have seen in a math class, but very likely have forgotten how to do. And that's fine, because you don't have to do that. You can just use this version where that work has already been done for you, and you're just solving for the value of B that you don't know. Okay, and you're actually solving for the ratio. You want to solve for the ratio of brightness between these 2 stars, Vega and Gaia DR2. All right, and so you would plug their apparent magnitudes in for the values of M. Look at the example in the book, but this is the equation to use. Okay, so that's what you need to use, just that equation for number 1. Number 2 is just an extension of that idea, because I talk about the power output of the sun on a solar panel. And so power is directly related to brightness. Now you might be thinking, well, didn't I make a big deal that brightness is subjective? Yes, but we're a certain distance from the sun, and that means a certain amount of energy arrives to us from the sun. Okay, so that's the actual power that reaches Earth. If we need to know the total power that the sun produces, we need to know how far the sun is from us. But we can still measure how much power gets to us. Okay, and it turns out that 1,360 watts of energy arrives per 1 square meter on Earth from the sun. So the idea then is that the ratio of power from the sun compared to the moon, because here that's the comparison that's making, must be equal to the ratio of the brightness of the moon and the sun in Earth's sky. Because if the sun is much brighter than the moon, then it means that it's delivering much more power per square meter to something like a solar panel. Okay, so that's the idea. Is you're going to use this ratio of powers and set it equal to a ratio of brightnesses. Now, in order to find the ratio of brightnesses, you're going to use the magnitudes, because I give you the magnitude of the sun and the moon, respectively. Use those ratios of magnitudes, which are the M values, to find the 2 B values, plug the B values into this formula, and use the one known power, the 1,360 watts, and solve for the power output that you would get from the moon. It should be a much, much smaller value. Okay? Even though the moon is relatively bright, it's the second brightest object in the sky, it delivers drastically less power than the sun. And indeed, when you run the calculations here, you will find out how much less power the moon delivers and why we never talk about using lunar panels as opposed to using solar panels. Okay? All right, so hopefully those equations will get you started. Again, really, this is all you need is just these two equations exclusively. The first one for number one, and then for number two, you're going to combine equation number one with the equation, the ratio that I gave you. Okay? All right, so hopefully that all makes sense. Thank you so much for watching this look ahead video, and I'll talk to you all soon. Bye for now.